Hello everyone. In this lecture we will discuss magnetic vector potential. So in magnetostatic we know that is divergence of magnetic field is equal to 0. So here when divergence of magnetic field is equals to 0, then B is equal to del cross A. Here this A is a vector potential. So here this A is the vector potential or magnetic vector potential. Now here we will discuss this vector potential in terms of current, that is in terms of line current, surface current or volume current. So let us start with the first, that is vector potential for line current. For line current, this vector potential A is equals to mu naught over 4 pi, and here we have I over R dl. So here I is the vector quantity. Then for surface current, this A we can write this is equals to mu naught over 4 pi, and here we have vector K over R dA. Similarly, for volume current, this A is equal to mu naught over 4 pi, and here this is a J over R dV. So these are the questions for vector potential for line current, then for surface current, and then for volume current. So now interesting question here is why we are interested for this vector potential. Why we are interested? Because these vector potential equations are somewhat easier to work with than the Biot-Schwarz law. That is, we can easily solve the sum problems with the help of vector potential as compared to Biot-Schwarz law. In continuation of this, we will discuss multipole expansion of vector potential. So here in this case we are interested to write the potential in the form of a power series. The form of a power series in 1 by R. So here I will repeat the same. In the multipole expansion of vector potential, we are interested to write the potential in the form of a power series in terms of 1 by R. For this, suppose here we have a current carrying loop. Current here is a steady current, and suppose this is a small segment, that is di, and here we have central point. Suppose this is central point, and this distance, suppose this is a r dash, and here we are interested to find the potential, and this distance is r from the origin, and this distance is, suppose this is a r cap, and this angle is theta. Okay, so in terms of here 1 over r cap is equal to 1 over r square plus r dash square minus 2r dash cos theta. Okay, or we can write like this, that is 1 over r summation n equals to 0 to infinity, and here we have r dash over r the power n, and this is Pn cos theta. Okay, so here 1 over r cap is equals to 1 over r summation n equals to 0 to infinity r dash the power r dash over r the power n Pn cos theta. So we know that is vector potential AR is equal to mu naught I over 4 pi, and here we have di vector over r cap. So now we will substitute the value of 1 over r cap in this equation. So we can write mu naught I over 4 pi, and here 1 over r cap is equal to 1 over r summation n equal to 0 to infinity, then r dash over r the power n Pn cos theta, and here we have di factor. Or we can write like this, that is mu naught I over 4 pi and summation n equal to 0 to infinity, or 1 over r the power n plus 1, and here integral r dash the power n Pn cos theta and di. So now we will expand this equation, that is limit vary from n equals to 0 to infinity. So first point here is mu naught over I over 4 pi. So here when n equals to 0, then we can write this 1 over r, or here, because r the r dash the power n equals to, here n equals to 0, so this term is equals to 1, so we can write this is a di, plus when n equals to 1, then we can write 1 over r the power 2, and here because n equals to 1, so we can write r dash cos theta di, and so on. Similarly, we can substitute value of n equals to 2, 3, 4 and so on. But here this we have, this is a closed integral, because this is a closed integral, so this term is equals to 0. This shows that monopoles does not exist. Okay, this is a well-known concept. So here we have only this second term. Suppose we ignore the higher terms, then I will repeat the same. Here first term is equals to 0, and we have only this second term, and suppose we ignore the higher terms, then we can write a dipole. This is a r vector, and this is equals to mu naught I over 4 pi r square, and this is equals to r dash cos theta di. Okay, so here when n is equals to 0, then we have a monopole, and when n equals to 1, then we have a dipole, and similarly we have a quadrupole and so on. So here in this case we consider only the vector potential due to dipole, that is mu naught I over 4 pi r square r dash cos theta di. Then we can write like this, that is mu naught I over 4 pi r square. So here we can write like this, that is r cap dot r dash, and this is a di. Okay, but here this r cap dot r dash vector di, that is this term, is equal to minus r cap cross dA. Now substitute this value in this above equation, then we can write, that is a dipole are equal to mu naught I over 4 pi r square, and here r cap cross dA vector. Okay, so further we can write mu naught over 4 pi r square, this is a r cap, and here we have this I dA vector. Clear? So here this ID, that is current into dA, is nothing, this is equals to m. And what is m? M is the magnetic dipole moment. Okay, so finally we can write vector potential due to dipole is equal to mu naught over 4 pi r square, and here we can write r cap cross m, or mu naught over 4 pi, and we can write this is a vector quantity, so we can write m cap cross r cap over r square. So finally the vector potential due to dipole is equal to mu naught over 4 pi m vector cross r cap over r square. That is, here vector potential due to dipole is equals to this. So vector potential due to dipole is dominating term in the multipole expansions. So for most of the practical purposes we can use this relation as a vector potential, but the total potential is equal to sum of vector potential due to dipole, then due to quadrupole, and then due to octopole, and so on. So here, as we discussed, when n equals to 0, then we have a monopole. So physically monopole does not exist. So total vector potential is equals to sum of vector potential due to dipole plus vector potential due to quadrupole and plus vector potential due to octopole. So dipole is due to when n equals to 1, quadrupole when n equals to 2, octopole when n equals to 3, and so on. I will repeat the same. For most of the practical purposes we can use the vector potential due to dipole only as a total vector potential. Okay, thank you.